Welcome to my presentation on the climatology of gravity wave activity in the middle and upper atmosphere as simulated by a whole atmosphere gravity wave parameterization and comparison with SABER timed satellite observations. Atmospheric gravity waves are known to drive the middle and the upper atmosphere. In this study, we will be using a general circulation model, implementing a whole atmosphere gravity wave parameterization to study the effects of a latitude-dependent gravity wave source distribution on the middle and upper atmosphere. The primary role of gravity waves is to control the vertical coupling between the lower and the middle and upper atmosphere. You can find the accepted article in Frontiers in Astronomy and Space Sciences, and I have uploaded an ArXiv version that you can see for further details. Gravity waves are everywhere in the atmosphere. They drive the small scale and large scale variability in not only the lower atmosphere, but in the middle and the upper atmosphere as well. This is a reanalysis picture of gravity wave variability in terms of horizontal wind divergence variations. Gravity waves are extremely difficult to model. However, observations provide a good overview of the concentrations of gravity wave activity around the globe. We have very good satellite observations of gravity wave activity at 30 kilometers, at 90 kilometers, and in the thermosphere at 250 kilometers. As you can see, the gravity wave variability in terms of momentum fluxes or density fluctuations vary as a function of latitude, longitude, and altitude. So this is a three-dimensional problem that requires GCMs in order to fill the gaps between these observational regions. It's been already modeled, it's been indicated by GCMs that gravity waves propagate into the thermosphere and produce large acceleration and deceleration in the thermosphere at high latitudes, not only in the MLT region. Our main tool is the whole atmosphere gravity wave parameterization combined with the GCM, the coupled middle atmosphere and thermosphere model. And we use SABER timed observations in order to produce a proxy for latitude dependence of gravity wave spectrum. So this whole atmosphere gravity wave parameterization is a physics-based gravity wave parameterization that includes dissipation due to molecular viscosity, ion drag, nonlinear interactions between the different gravity wave harmonics, radiative damping, and eddy viscosity. Now, here what you see is the spectra that we have used in our modeling study. Experiment 0, 1, and 2 are different gravity wave spectra at 15 kilometers, compared with a symmetric case here. The default spectrum is experiment 0, the black line. The latitudinally adjusted spectrum is experiment 1 in blue, but it's shifted 10 degrees by 10 degrees in latitude towards the southern hemisphere pole, towards the south pole. And the peak gravity wave momentum flux is increased by 50%. In experiment 2, it's increased by 100%. Now, it's important to quantify first how the mean circulation responds to changes in the gravity wave momentum flux distribution. We have 3 simulations, 0, 1, and 2, and compared with UR's zonal winds. The model simulates the mean circulation pretty reasonably. However, we do see differences in the different model simulations with different momentum flux distributions. Increasing the gravity wave momentum flux sinusoidally produces response in the middle and upper atmosphere. But the main response is in the MLT region, where the eastward winds in the southern hemisphere, for example, are significantly decelerated here. Now, looking at the gravity wave drag gives us an idea how the effects of the gravity wave change with changing momentum flux distribution. For experiment 0, 1, and 2, again as latitude, altitude distributions, the main finding is that, for example, in the southern hemisphere, the westward drag is strengthened at lower altitudes, but it's weakened at higher altitudes. There is also some degree of response in thermospheric drag at high latitudes mainly, where the majority of the gravity wave effects are concentrated in the upper atmosphere. Looking at the temperature distribution, we identify, presented exactly in the same way, 0, experiment 0, 1, and 2, altitude-latitude distribution, superimposed. So the black contours are the actual neutral temperatures, the colors are the temperature differences. We see that the major response is in the high latitude southern hemisphere, where we have an enhanced gravity wave drag due to the modification of the gravity wave spectrum in the lower atmosphere. The relative temperature changes are up to plus minus 10% in the middle atmosphere and plus minus 1 to 2% in the thermosphere. So overall, there's evidence that there's direct primary gravity wave propagation into the thermosphere, and there are global effects due to gravity wave dissipation and saturation. We've implemented a latitude-dependent gravity wave spectrum into our gravity wave parameterization and thus into the GCM. There are noticeable changes in the MLT region. Gravity wave activity in SABER is in terms of absolute momentum flux. There is no directional information. Gravity wave parameterization, however, includes momentum fluxes in terms of directional momentum fluxes and phase speeds. SABER includes a broad spectrum of waves. The gravity wave spectrum used in the gravity wave parameterization is rather narrow, and it's concentrated on the unresolved gravity waves. This is what a gravity wave parameterization does in general circulation models. Therefore, comparison of satellite observations with general circulation models should be done very carefully. We have also found out in our analysis of mean circulation that the response of the upper thermosphere is less pronounced to changes in the to the momentum flux of gravity waves compared with the response of the middle atmosphere. Thanks very much indeed for your interest.